So I will start today's lecture. But before that, I have one notice. So before proceeding the final term project, we have to make a team. So this is the team making sheet that I shared yesterday. So you have to put your name in one of these slots. Okay. So if you have friends, if you have already friends in this class, then you can gather those friends to make a team and write down the names together. But if you don't have any friends, don't worry, and you can put your name in new team slots. Okay, then we will help you to make a team. Okay. So I will request you to make a team by, anyways, write your name in this sheet by this Friday, okay? So that we can help you to make a team, to finalize a team by next week, okay? So maybe one third of students are writing their name here, but remaining are not yet. So please do this quickly, okay? Maybe, and also the final project that will be announced today, okay? And also the quiz one score was announced in the blackboard, okay? So if you think something is wrong, then please mail me, okay? I will confirm why your score is like that, okay? Okay, so I will start today's lecture. So we are learning the real-time pipelines for object detection, okay? So previously there was a two-stage method and also the DTR-based method, but those are too slow. So I introduced this YOLO, which is the real-time object detection pipeline, and they are one-stage algorithm. They are simultaneously estimate the bounding boxes and also the class probability for each grid, and then do some post-processing called as NMS, non-maximal suppression, to finalize their bounding boxes. This is YOLO, which is very simple to implement, and their learning speed is very fast. Okay. But the problem here is they are exhibiting low recall, which means they are not fully covering the ground truth inside an image. I mean, I will introduce about the concept of recall and precision here. So those are two measurements frequently used for evaluating the performance of the machine learning system. So recall means the coverage of the ground truth. So it means if there are total ground truths in the image, for example, there are two bounding boxes as the ground truths, then the recall means how many ground truth boxes are covered by the prediction. If you estimate just one bounding box like this, then the remaining one ground truth is not covered by your prediction. So yeah, the recall is calculated like this. I mean, the covered ground truth over all the ground truths. Okay, how many ground truths are covered by your prediction? That's the recall. And precision, it means number of total prediction. And here, number of correct prediction. That's the precision. Okay, so among you predict how many are correct. That's the precision, but recall is somehow different. So, I mean, let's say, let's exemplify this kind of thing. So, if let's assume there are two persons, and one person she speaks a lot, okay, and the other person he speaks less, okay, maybe just few words in a day, but she speaks a lot of words. Okay, so we can say here we can say this is the like the system, the object detection pipeline that predict like maybe 1,000 bounding boxes. Okay, and also we can say this is the object detection pipeline that predict only few, maybe 5 bounding boxes. Okay, so he predict less, but she predict a lot. Okay, and among the bounding boxes, she predict maybe maybe half can be correct. Okay, so among all the bounding boxes, half can be correct. Then her precision might be 50%. Okay, but among these 5 bounding boxes, let's say he predict very good. I mean, 4 bounding boxes are correct, let's say, then his accuracy, his precision is quite high. His prediction is 80%. But in this case, the prediction precision is 50%. Okay. But let's say there are, let's say, 30 ground truth bounding boxes in the image. Then if she predict 1,000 bounding boxes, and among that 500 bounding boxes are correct, then there could be many redundant boxes, and let's say it intersect with 20 ground truths, let's say. Okay, then the recall in this case might be 20 over 30. Okay, it might be 66% maybe. Recall is 66%. But in his case, he predict 4 bounding boxes, and let's say this coincides with 4 ground truths. Then his recall might be this. Okay, maybe this is around 12%. Okay, so I mean, both are not that I mean good situation, but I mean, if you choose one, then might be this. Even though the precision is less, this is more preferable because even though the precision is high for this system, but it is not, I mean, properly covering all the ground truth boxes in the original image. So recall is quite low. So even though the precision is very high, because the recall is very low, this system is not that critical. But I mean, this system is better maybe, even though its precision is low. It can, I mean, on average, cover, I mean, more than half of the ground truth. So maybe we have to select this system. Okay. So when considering the performance of the system, especially for the object detector, we have to consider both precision and recall. Okay. So that's the recall and precision. Okay. So are you guys understanding this? The difference between recall and precision. So I mean, YOLO, its precision is comparable to fast RCNN. Okay, but because it predicts only 98 bounding boxes, okay, as the output, so basically its recall is bounded by this number. Okay, so if there are more than 100 objects, then YOLO will miss all remaining I mean objects. Okay, because their number of bounding boxes are limited. So that was the weakness of the original YOLO. We normally call this as YOLO version 1. So if you see this graph, you can feel like that RCNN, fast RCNN, and faster RCNN, those are located here, and YOLO is here. So here, this is the showing their speed, okay? So FPS. So if this number, if you go this way, then it means the algorithm is becoming faster. And this y-axis denotes the accuracy, actually the precision. Okay. So if it goes this way, go up, it means the pipeline's precision is becoming better. Okay. So RCNN, faster RCNN, faster RCNN, and faster RCNN, it is located like this. So becoming, adding faster, it becomes become faster, okay? Compared to the RCNN, original RCNN, the fast RCNN is slightly in the right side, and faster RCNN is slightly, more in the right side, okay? And their accuracy is becoming better and better, okay? When developing, when from RCNN to fast RCNN and faster RCNN, their precision is becoming better and their speed is becoming faster, okay? And actually, this line indicates that in the right side of this line, it means non-real-time pipeline, and in the right of this line, it denotes the real-time pipeline. So the criteria is 30 FPS. Okay, so we normally say if the algorithm exhibits FPS larger than 30, then we call that as the real-time pipeline. Sometimes we use the 20 FPS as well. So this 20 to 30 FPS, those are criteria for measuring the real-timeness. Okay, so YOLO is definitely faster than having the larger FPS than the 30. So we can call YOLO as the real-time pipeline, but we don't call this RCNN-based method as the real-time. We don't call that as the real-time pipeline. Okay. So this is the YOLO version 1 we have learned so far. Okay. So it predicts only 98 bounding boxes, and their recall is also limited. Okay. And basically, the performance of the YOLO is less than the RCNN-based ones. Okay. But they are very fast. That's the characteristic of the YOLO. But things are becoming changing because YOLO is originally introduced in CVPR 16 in the year of 2015. Okay, but after that, researchers are continuously trying to improve this YOLO version 1, and nowadays we have YOLO version 12. Okay, so recently we got YOLO version 12. Okay, so there have been a lot of improvement in the YOLO version. Okay, and already for the YOLO version 2, their speed is remained real time, but you can see their accuracy is already becoming better than the faster RCNN. Okay, even though they are real time, YOLO version 2 have made this pipeline works better than the RCNN-based method. Okay, so thanks to this good characteristic, the real-time speed, and as well as the good performance, the industry nowadays becoming more and more using this YOLO pipeline, implementing the practical pipelines. Okay. Okay. So today I will introduce how what kind of things have been added to the original YOLO version 1 to extend it to be better than the original YOLO and even better than faster RCMS. Okay. But mostly those techniques are heuristics, not that fancy actually. They are using some of the heuristics, which seems like some tricks to improve the performance of the YOLO version 1. Okay. Anyways, I will introduce that. Okay. And actually, the YOLO is maintained. The original YOLO of, the original author of YOLO version 1, he maintained the YOLO version 1 through YOLO version 3, okay? But he actually finished maintaining this YOLO anymore because he say he's afraid of, utilizing this pipeline towards like a war, okay? So he quit actually the research on this pipeline. And after YOLO version 3, other guys, other researchers are maintaining YOLO. So nowadays it reaches the YOLO version 12. And actually their performance is getting better. And also they are also, including some new features like pose estimation and others, okay? And also the segmentations, okay? Anyways, this is the brief history for the YOLO, okay? So when reading the YOLO version 2, you can see this kind of graph. So there are multiple heuristics added to the original YOLO version 1 to make it better than, to make it to YOLO version 2. And you can see this MAP, which is the measure for the precision, is greatly improved. Okay, YOLO, original YOLO, their MAP on VOC 2007 data was 63.4, but YOLO version 2, their accuracy is becoming better than that of the YOLO version 1. Okay. So this, I will introduce which kind of tricks are introduced to make it better than YOLO version 1. And also, especially for the some scheme, like the anchor boxes, you can see when adding one schemes, you can see their accuracies are gradually improved. Okay, so if you use these 2 and 4, without this component, most of schemes, when adding new scheme, their performance is getting better than previous. Okay, but you can see this part. If you add these 2, especially for the anchor box scheme, you can see their MAP is becoming less. Okay, so then you can ask why these anchor boxes are used. Okay, but this is the thing related to the recall. So MAP is the measure for the precision. Even though the precision is slightly reduced, when using the anchor box, the recall is 7% improved. So here, the recall was 81%. But here, even though the precision is slightly reduced, their recall is 7% improved. Okay, so because of this, people are using this. The author of this paper is using the anchor box. Okay, and also you can see here the anchor boxes are missing. So in the final YOLO version 2, they are actually reporting the accuracy MAP without the anchor box, but they are saying here their MAP, when using the anchor box, the MAP is not changed, okay? They are actually retained, but they can obtain better recall. So in the final YOLO version 2, they are using anchor boxes, okay? So from now on, I will introduce the one schemes, okay, by one scheme. So there are several schemes added, but I think the most important scheme is the anchor box, okay, but others are rather heuristic, but I will explain that. One of the important changes that make YOLO becoming better than YOLO version 1 is the use of the batch normalization. But this is not their contribution, but there have been some paper that try to use the batch normalization for the deep learning trading. So they use those schemes when training the YOLO network and find that their trading is becoming stable and actually their MAP is getting better. So when using batch normalization, the MAP is 2% improved. Okay. And what is batch normalization is this is the scheme designed to prevent the overfitting. Okay. And also, this is not the scheme especially designed for the overfitting, but they have the effect of preventing the overfitting. Okay? But the aim of this scheme is initially this batch normalization have been proposed to prevent this kind of phenomenon, the covariate shift, which means this is the deep architecture having multiple MLP layer and nonlinear layer. Okay, this is the deep architecture. When training this deep architecture, the the scale of the layers, I mean, their scale is not stable. Okay, so I mean, this is the input you can get the overall input distribution, then you can draw it like this. Okay, so maybe the input is the vector, right? And if you draw those vectors distribution, then their scales are like this, let's say. But if you pass those inputs to several layers and then again draw the distribution of responses, then you can observe that their scales are arbitrarily transformed. Okay, so this is frequently observed during the deep learning training. Okay, and also after another deep layers, if you draw their distribution, responses distribution, they are again transformed in arbitrary way. Okay, so I mean this kind of the scale changes is not desirable when training the deep learning, because due to this these scale changes, I mean, the important the response, those variations cannot be captured because of sometimes these scale changes are overwhelming the subtle variations in the feature space. Okay, so this kind of data distribution, enveloped data distribution changes are not desirable. Okay, so in the batch normalization, the thing they want is they actually normalize. This is the normalization technique. So they actually normalize the scale of the responses to the normal distribution. So this is the arbitrary distribution of the responses. Okay, their scale can be arbitrary, but you normalize those scales into standard normal distribution by subtracting the mean and divided by the standard deviation. You can transform the original response to the standard normal distribution. Okay, so this kind of normalization is done between right after the convolutions, okay, or the MLPs. Okay, that is the idea of the batch normalization. And also, why batch is coming here is the mean and standard deviations are calculated for each batch. Okay, so batch is the unit that parallelly process the deep learning. So normally 32 images or other small number of images are processed together, and they are called as the batch. And this mean and sigma, the standard deviations, those are calculated for each batch. Okay, and they are normalized. The samples in each batch are normalized using this mean and standard deviation to stabilize their scale variations. Okay, so when transforming the responses to this type of scale normalized space, we can capture more subtle variations according to the input variations. Okay, this kind of scale variations are too abrupt, so we cannot capture sometimes the changes in input variations. But now we can stabilize the other component and can capture subtle variations. Okay, that's the idea of the batch normalization. So this is known to be robust to the deep learning architecture. So I mean, actually, when using this batch normalization, the training becomes faster than before. Okay, so nowadays many people are using this scheme, and also we do not have to use dropout layers when using this batch normalization, because this is already very good for giving some randomness during the training, and it can prevent overfitting. Okay, so it has very good characteristics. Okay, so as I told you, for the mini batch, these responses, we get the mean average values, and also the response for the responses, we calculate the variance. Okay, and then for each response in the batch, we subtract the mean and divide it by the standard deviation to get the normalized response. Okay, so this is having the normalized scale, so it can be helpful for faster trading, okay, by capturing subtle variations in the input space. That's the idea of the batch normalization. And actually, this batch normalization is not the contribution of this YOLO. There are already trends to use this batch normalization to accelerate the training of the deep learning in this maybe in the 2017s to 2080s. So YOLO version 2, they are just using this scheme and find that their MAP is getting better. Okay, but I mean, in general, batch normalization is good to know. Okay, and the other scheme is tricky. I mean, in YOLO version 1, their baseline architecture was the VGG16, okay, which is the image classification network. Okay, And their network input size was 2 to 4 by 2 to 4. So we already learned about this VGG16 network, and we already know that their input image, their scale is this, okay? But YOLO, for the YOLO, we are using 448 by 448 images, this dimension as the input dimension. We are using this as the input dimension because for the image classification, their whole images having just one object inside, okay? And we use VGG16 network to infer some semantic label, okay? So basically, the image classification, it has just one object. So its scale can be small. But in YOLO, we have to detect multiple bounding boxes. And because of that, normally the images have to be bigger in scale compared to the image classification task. So we actually, the YOLO version 1 have used 4 times larger. So if this is 448, then this would be 2 to 4 by 2 to 4 image. And there are 4 times actually larger than, their image size is 4 times larger than that of the YOLO version 1. That of the VGG16 in YOLO version 1. But thing is, they are just enlarging using the same VGG16 architecture. Previously, for the image classification task, they do this kind of probability estimation, okay? But in YOLO version 1, they are using enlarged input images as the input to this VGG16, but in the middle, they add some more modules to estimate both class probability and also the bounding box. Okay, using the same architecture for enlarged images. Okay, and this YOLO version 2, the authors are arguing that there is some gap between these two input scales. Okay, so these sized images, so when we input this sized enlarged input image, then there could be some difference, and it offers some suboptimality. So they actually fine-tune the original VGG16 network at the full resolution for 10 epochs on ImageNet. So previously, this network is trained by rescaling all the data in the ImageNet to 2 to 4 by 2 to 4. Okay, but to use it for the YOLO, they do this kind of fine-tuning. They upscale the original ImageNet data to this size, 448 by 448, and fine-tune the network for 10 epochs. And using this simple scheme, the MAP has been greatly improved. Actually, full MAP has been improved. Okay. 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 So this is the VGG16 used for 2 to 4 by 2 to 4 image. But this is the YOLO used for 448 input images. Okay. In the last layer, it estimates 1,000 dimensional vector, which is the 1,000 dimensional probability for 1,000 classes when used it for the image classification. But YOLO, it adds some other modules to estimate the bounding box information and also the class information for each grid. Okay. So you are seeing the difference, but only the last part has been changed. So in the middle, the coefficients are not that changed. So they fine tune actually the original VGG using these upscale images to improve the performance. Also, previously in YOLO, there are FC layers. Okay. So anyways, in the last layers, there have been FC layers, and also there are pooling layers to reduce the scale, okay? But instead of this FC layer and pooling layers, uh, the authors of the YOLO version 2, they are involving convolutional layers, okay? I mean, pooling layer, if you use, for example, 2x2 pooling, then the original signals their dimensions are halved, okay? But when you use the convolution operation with some filter, but with stride 2, then this is also can reduce the dimension of the input signal by, I mean, it can halve the input size, okay? So convolution, but I mean, pooling layer, it doesn't have any parameters to learn, and it simply reduces the dimension. Okay, it can sometimes lose the information, but the convolution layer, it can convert filter to the original input, but using stride 2, it can at the same time reduce the dimension. So in that sense, the authors are thinking that convolution is not losing more, I mean, less, it is losing less information compared to the pooling layer. So that's why they replace the pooling layer to the convolution layer. Okay. And also, FC layer is sometimes slow. So convolution operation is basically they are using 2D operation and little bit faster than the FC layer. So they are replacing this FC to convolutional layer. Okay. So this is very small design changes, and this can slightly compensate for the I mean the MAP. Okay. But I mean, here you can see when using this convolutional operation and also the anchor bars, their MAPs are slightly reduced, okay? But without this convolution, the MAPs are maybe more reduced, but it is compensating the MAP reduced, okay? And the next thing is the anchor bars, okay? This is very important contribution of YOLO version 2. Actually, this is related to increasing the recall. Okay. So as I mentioned to you, YOLO is suffering from the low recall because it estimates only 98 bounding boxes. Okay, when the grid is 7x7, and if from each grid we estimate 2 bounding boxes, the number of bounding boxes from an image is the 98. Okay. So we only estimate 98 boxes in YOLO version 1. But this anchor boxes is proposed to increase the amount of bounding boxes estimated from the YOLO pipeline. Okay. So and also we are changing our architectures by removing the pooling layer and also the FC layer, and instead use the convolutional operation. We can adjust the dimension of intermediate feature to the feature to be 13 by 13. Okay, originally we used the 448 by 448 dimensional input image, okay, and that will give us 14 by 14 feature space. 2D features, okay? And the anchor boxes means is for each 2D feature pixels, we by centering this 2D feature pixel, we estimate 5 bounding boxes. Okay, that's the these boxes are called as the anchor box. Okay, by centering their center as the 2D features, each pixel, we estimate 5 bounding box for each feature pixels. Okay, that's the anchor box, and there would be 5 bounding box for each 2D feature pixel, and there are 13 by 13 2D feature. Originally, there are 14 by 14 by 5 2D feature. So this amount of bounding boxes are estimated from YOLO version 2. Okay, compared to 98, this amount of bounding boxes are quite many. So now we can solve the problem of low recall in the YOLO version 1. Okay. So on purpose, they are explicitly proposing this scheme to increase the number of bounding boxes. Okay. But as I mentioned, if you use this dimension as the original input image, then because the dimension of the using the pooling intermediate layers, the CNNs tend to reduce your input dimension by 32 times. So if you use 448 by 448 images, then intermediate features should be 14 by 14 size. Okay, and it have to produce this amount of bounding boxes. Okay, but the authors are on purpose try to change this 14 to 13. Because and to do that, to achieve that, they on purpose reduce the original input size, okay, to 416. So actually 42 times reduced, okay, to amend the dimension of 2D feature size. They on purpose amend the input image size. Okay. This is because this is their argument, the author's argument that this width and height of the 2D features have to be odd numbered. That's their motivation to change this 14 to the 13. Because when your width and height is odd numbered, there are 1 pixel in the middle. Okay, there are center pixels in the middle, but if your width and height are odd, even numbered, there is no center pixel. Instead, there are 4 pixels in the middle. Okay. So are you guys following this? So when, for example, when width and height is 13 by 13, there are 1 center pixels here. But if it is 14 by 14, there should be 4 pixels in the middle. Okay. But in the original image, there will be, there are high probability to have the center object inside the picture, okay? Because we humans are taking pictures by focusing on object, main object, okay? And we tend to focusing those main object in the center position, right? So this kind of center object is well captured by the bounding box from the center pixels, okay, right? So because of this, the authors wanting to keep the center pixels in the 2D feature space and wanting to keep the width and height of the 2D feature as the odd number. Okay. If they have even number the width and height in the 2D feature, they are slightly mismatched and from the center object, and it is becoming inefficient. Okay, slightly becoming inefficient, and the authors wanting to avoid those inefficiency. Okay, so anchor boxes, basically their idea is increasing the number of bounding boxes and wanting to increase the recall. Okay, so compared to this 98, almost 10 times more bounding boxes are used in YOLO version 2. So even though their MAP is slightly reduced, their recall here was 81%, but recall here is becoming 7% improved. Okay, so anchor boxes are used for that purpose. And also in the final model, when using this anchor box, the entire MAPs are becoming stable, but the recall is improved. So in the final model, final YOLO version 2, they are using the anchor box scheme. Okay. Are you guys following this? Okay. That's the yeah. So recall is becoming better from 81 to 88. And the other scheme is also heuristics, but good to know maybe. If you understand this, this might be maybe informative. So basically, we are estimating 5 bounding boxes from 1 pixels in the 2D feature, okay? And this, and the shape of the anchor boxes, those are human design, okay? So the aspect ratio of this anchor box and the scale of the anchor box, those are human engineered, okay? But what these dimension priors means, I mean, using the training data of these 2 benchmark, they, I mean, they collect all the ground truth bounding boxes and decide somehow apply the clustering, k-means clustering algorithm on the bounding boxes, okay, their shape and aspect ratio and scale. Then they measure according to the k values, the number of clusters values. They measure the IOU, okay, the ground truth, how many ground truths could be covered by the clustered bounding box, okay? And they find that 5 over 5, the IOU is becoming relatively saturated, okay? So, and also if you estimate more bounding boxes, it can cause reducing the real-time needs, okay? Reducing the speed and thereby failing to achieve the real-time needs. So considering those kind of time complexity and also the MAP, the accuracy, the 5 number of bounding boxes could be 5, okay? So they decided as 5, and at the same time, the aspect ratio of the bounding box and the scale of the bounding box, those are predefined by applying the 5 means clustering on the training set bounding boxes, okay? So they use some before these dimension priors for the bounding boxes, they arbitrarily design these 5 bounding boxes estimated from each pixel of the 2D feature. But now they use some of the aspect ratio from the data, okay, and becoming slightly better than previous. Okay, so when using this dimension prior and also this kind of location prediction, you can see MAPs are greatly improved. So I will introduce this location prediction again. Okay, so this is the dimension prior for deciding 5 bounding boxes, scale and aspect ratio. Okay, that's actually data-driven thing. Okay, and also when predicting the location of the bounding boxes in Europe version 1, they are directly estimate their center position and also the how to say the bounding boxes height and width. Okay, and also the confidence value. Okay, we have to estimate this for each grid in YOLO version 1. So this is the center X, center Y, and width, height of the bounding box, and confidence value. This is the 5-dimensional information which is inferred for each bounding box in original YOLO. They, in original YOLO, they estimate the low values of the center positions and width and height of the bounding boxes, and also the confidence. But in here, because we already find the bounding box scales and aspect ratio, those are PW and PH. So the bounding box width and height are coming from these data-driven values. So this is the value we find from this dimension prior. Their width and height are coming from the data-driven values, but we estimate this TW and TH, and we adjust their somehow ratios from these predefined bounding box scales. Okay, by adjusting these things, we make new bounding boxes. Okay, and also their center coordinate here, Bx and Y, which denotes the center coordinate of the bounding boxes. We do not use the raw values estimated from the network. Instead, we apply sigmoid on this Tx and Ty and at the center positions of this grid location. So this grid location is predefined. So if we want to estimate 2 bounding boxes for this grid, then these values are becoming Cx and Cy, and we only estimate their offsets from this grid cell left top coordinate. Okay, that's the new way to calculate this Bx and By, which are the center position of the bounding boxes. And also this confidence value that I already explained is actually same as before. So TO is applied with sigmoid, and this becomes the value between 0 to 1. Okay, and actually this is denoting the objectness multiplied by the IOU between ground truth and prediction. Okay, and using this we apply the NMS later. So anyways, this location is now, more accurately predicted from this network output. Okay, so it is becoming slightly better than before. So combining this dimension prior and location prediction, the MAP is becoming better. Okay, and another important idea is this pass-through. Okay, and also the multi-scaleness. Okay, this is actually important ideas, but this is rather heuristics. Okay, also these are also rather heuristic ideas, but anchor boxes is very important. Okay, so then I will explain what is the multi-scale training. As you know, original YOLO uses the 448 by 448 images, okay, as the input, okay. But YOLO version 2, to make the intermediate feature to have the 13 by 13 dimension, we change their input size from 448 to 416. Okay. So YOLO version 2, it uses the 416 by 416 images. Okay. But they are adding few more skins on this. Okay. Instead of fixing input image size to this, they try to change the network input every 10 batches during the training. Okay. And the possible input size they are using is this kind of multiple resolution image, but their offset is 32. Okay, so next is this, next is 416, next is 48, and next is 480, next is 420, 512, next is and sorry. Okay, and 608. So there are actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 scales used. When training, during training only, they are using this kind of technique. Okay. So this kind of multi-scaling, giving some multi-scale information is helpful to, improve the accuracy of the object detector. So this is the reason why, the authors of the YOLO version 2 is using this. So during training, they are resizing the original input image size to this and training the network once, okay? And then we scale that to the other dimension and training for 10 batches. And we scale to another dimension and retrain, okay? This is the way to improve the accuracy, okay? So actually by doing this multi-scale, they can improve the MAP by 1, okay? And also, pass-through network that is explained later. So, and also they use another architecture than the VGG16 network. Okay, so maybe this have to be explained before when explaining these convolutions. Okay, sorry, this is too. So new network that is here, okay, when using the new network, before using the new network, and after using the new network, the performance is slightly improved. At the same time, the new network, whose architecture is called as the darknet, instead of the VGG16, they are using darknet, and this 19 is named because it has the 19 layers inside. It is faster than VGG16, but it increased the MAP as well. So they are using this new network. Okay. So they are proposing this kind of new network, and their main difference is instead of the FC layer, they are using this average pool. Okay, FC layer is sometimes time consuming, so they remove those FC layer, instead having convolutional layer and also the average pool. Okay, and overall they have 19 layers, so they call this as darknet 19. And also they try to use the batch normalization, and also they adjust the filter, their size into 3 by 3. Okay. So they are having the slightly different network and can accelerate the model speed and also improve the MAP as well. Okay. And this is the result for multi-scale training. So for the same YOLO version 2, if your input size is changed, for the same testing data, that their MAP is changed. Of course, their FPS is also changed due to the, image. If you have more image pixels, then your speed is getting less. Okay, so the speed is getting less, but the accuracy could be better. So because of this, you fix the image size as this during the inference to keep the real-time needs, but try to supply multi-scale images during the training to give more information to the model from the multi-scale needs. Okay, that's the multi-scale training, and this is a quite important skill. Okay, but it improves performance with 1% increasement, which could be minor, but the idea itself is very interesting. So this is the YOLO architecture. This is original YOLO input image having this dimension, and there are multiple convolutions to make the final output. Okay, but in the middle, you can see their two-dimensional 2D dimension is reduced, tend to reduced, but sorry, their two dimension in 2D space is becoming reduced, but their channels are becoming larger. Okay, and by combining these intermediate intermediate features having larger dimension, 2D dimension. If we combine this information by reshaping this to have the larger channel and concatenate it with the subsequent responses, and by concatenating this to infer the later responses, then the performance is becoming better. So that's the idea of the pass-through layer. So they concatenate the higher resolution features with the low resolution feature to have more abundant information about the images. Okay, so when achieving the object detection task, actually, I already mentioned this. So from given image, the object, their size could be arbitrary. Some object could be very small and some object could be larger. Okay, so to capture this kind of multi-scale needs of the object, this kind of scheme can be benefited. Okay, and also this kind of multi-scale training, those are effective as well. Okay, but this kind of pass-through layer, having this pass-through layer is also helpful for solving this kind of object scale problem. Okay, so this is the multi-scale and pass-through, and you can see their performance is consistently improved. Okay. So high resolution detector, this is similar to high resolution classifier, and it can achieve us to obtain the YOLO version 2 from the YOLO. Okay, so, but I mean, the most important thing would be anchor box and also the pass-through, which serve the multi-scale needs. Okay, but the rest is somehow heuristic, okay? But anyways, we can greatly improve the performance, okay? And we indeed surpassed the YOLO version 2, indeed surpassed the faster RCNN, which is the heavy architecture having two-stage algorithm. Okay. And YOLO version 3, that's also having more heuristics to improve the performance. Even it cannot be conference paper, but in the archive only. But I will explain this, continue explaining this in the later lecture. Okay. Thanks, and see you next Monday. Next Monday is holiday, so maybe we will see in next Wednesday. Okay. Thank you. See you.